In our last video, we left off discussing how to find the area underneath a curve. So we let f of x has to be a continuous non-negative function on the closed interval ab, and we define our partition on ab as breaking into n plus 1 little x values to have n subintervals, where we can find the width of each of those subintervals, which is the width of our rectangle, as b minus a over n, because we typically want to use uniform partition. Each xi is found by a, the starting value x0, and adding I number of partitions, I number of widths to it to get that, all the way up until we added n of them to get b. And then xi star is some value in the subinterval. It can be the right endpoint, it can be the left endpoint, it can be the midpoint. It's just some value in each of the subintervals. And so then when we plug that xi star into the function, that'll give us the height of the rectangle. The partition is the width of the rectangle, and when we multiply these together, that gives us the area of each of those rectangles. And then we add each of those, so we add from 1 to n rectangles, and the larger that n goes, the more rectangles we have, the closer we are to the area, actual area under the curve. And if n were to go off to infinity, and we had infinitely many of these rectangles, we would get the exact area underneath the curve. So let's take a look at an example. Let's actually revisit the initial question in our last video about the area bounded between x squared plus 1 and the vertical lines 0 and 1 and the horizontal line 0. I'll remind you what that looks like there. As we did in the last video, we used rectangles to approximate the area, but we never got the exact area, just about values that it was between. So let's now actually calculate the actual area underneath that curve. We're going to use uniform partition, and to start, we'll just let our xi star, our sample point in each of the intervals, be the left endpoint. So it'll be the left endpoint of this interval right here, so it'll be xi star. So then for our uniform partition, each delta xi is going to be the same, so we can just call it delta x if you want to. Find it by b minus a over n. Well, our interval is from 0 to 1, right? So it's 1 minus 0 over n, or 1 over n. So then each of our xi's is going to be a, which in this case is 0, plus I delta xi. So xi is going to be 0 plus I, right, times our delta xi we just found to be 1 over n. Put that all together, each xi is going to be I over n. So again, we're going to start by choosing our sample point to be the left endpoint. So x star I is going to be xi minus 1. So if xi is I over n, then xi minus 1 is I minus 1 over n. So now we can calculate the area under the curve. We're going to look as the number of rectangles goes off to infinity, and we're going to take the sum from 1 to n of this function evaluation, where we plug in this x star here, will give us the height of the rectangle, and this delta x right here is the width of the rectangle. So height times width gives us the area of that little rectangle, and as we add all of those sums of those rectangles up, as n goes off to infinity, that'll give us the area underneath that curve. So xi star, I remind you, is I minus 1 over n, and then we're going to multiply that by delta xi. Well, notice here delta xi is 1 over n. So to find the area under that curve, we're going to look at as the number of the number of rectangles shoots off to infinity. We have our height, which is the function evaluated at xi star, which is the left endpoint, I minus 1 over n, times the width of each rectangle, which is delta xi, which is 1 over n. Now remember what our function was. It was x squared plus 1. So to do our function evaluation here, f of x was x squared plus 1, so we're going to take whatever's in the parentheses here, squared, plus 1. So there's my height, function evaluation here, times my width is 1 over n. Now notice here that we're looking at the summation as I goes from 1 to n. 1 over n has no bearing whatsoever on I. I is completely unrelated to this 1 over n. So we can actually pull this 1 over n out of the summation. Just multiply it in. That's using that coefficient rule we talked about, and that coefficient just happens to be 1 over n. So we can pull that out of the summation. Now, what does it mean to square something? Times it by itself. When I multiply across, I'll multiply my numerators, I minus 1 times I minus 1, and multiply my denominators, n times n. And then I still have this plus 1. All right, well, let's distribute this out. I minus 1 times I minus 1 gives us I squared minus 2I plus 1, all over n squared, and then we still have this plus 1. So the area under that curve, we're going to look as the limit of n approaches infinity of this whole thing, including the summation. Well, here, taking this whole thing and dividing it by n squared is the same thing as dividing each of the pieces by n squared. So I'm going to separate that fraction out. And now one of our summation rules is that if you're taking the sum of terms being added and subtracted, you can actually just take the sum of each of those terms and add and subtract as you go along. So I can take the sum from 1 to n of this minus the sum of 1 to n of this plus the sum of 1 to n of this plus the sum from 1 to n of this. And just like we talked about before, the n squared has no bearing on the summation. The n squared and this 2 have no bearing on the summation, and neither does this n squared, so we can pull all those out, right? So I pulled out a 1 over n squared here, I pulled a 2 over n squared out here, I pulled out a 1 over n squared here, and now these are all summation formulas that have been discussed in class before. We have a formula for the sum from 1 to n of I squared, we have a formula for the sum from 1 to n of I, and this and this. So applying those formulas, that gives us the limit as n approaches infinity of that 1 over n from the outside, the 1 over n squared that was outside that first summation. Here is what the sum from 1 to n looks like of I squared. Minus 2 over n squared, this is the sum from 1 to n of I. Plus 1 over n squared, this is the sum of 1 to n of 1. Plus, this is the sum from 1 to n of 1. All right, so now what I'm going to do is I'm going to simplify. This n and this n squared will cancel down to 1n, and then I've got all of this right here, this n plus this n canceled, so n plus 1 times 2n plus 1 all over 6n. This n and this n squared will reduce down to 1n, and these 2's will cancel, so I'm left with n plus 1 over n. And then this n and one of these n's will cancel, and I'm left with 1 over n, and then I have a plus n. And now I have 4 different terms being added and subtracted. In order to add and subtract them, I'm going to need a common denominator, and it's going to be 6n, right? So multiply the top and the bottom here by 6, multiply the top and the bottom here by 6, multiply the top and the bottom here by 6n. Once all the denominators are the same, I can add and subtract their numerators over that denominator. Now, keep in mind, I'm subtracting this entire numerator, so I need to subtract the 6n and I need to subtract the 6. Now, when I combine all of my like terms from here, 2n squared plus 6n squared, 3n minus 6n, 1 minus 6 plus 6, it simplifies to 8n squared minus 3n plus 1. Still all over 6n. And I'm taking the limit as n approaches infinity. I still have this 1 over n out here, so let's go ahead and distribute that in to give me that 6n squared. And now we're taking a limit at infinity. This is something that we've talked about previously. So remember our little trick. We're going to divide everything by the highest power of, in this case, n, in the denominator. So n squared. So I'm going to divide the 8n by n squared, or the 8n squared by n squared, the 3n by n squared, the 1 by n squared, and the 6n squared by n squared, and reduce. And so now I'm ready to take my limit. As n goes off to infinity, 8 stays as 8. 3 over n will go to 0. 1 over n squared will go to 0, and 6 will stay as 6. So that gives me 8 over 6, or 4/3. So the area under that whole curve is 4/3. Which is about 1.333. Now, if you look back at the estimates we had come up with, all of our underestimates were under 1.33, and all of our overestimates were over 1.33, but as we added more and more rectangles, our areas, our estimates that we were using of the area under the curve got closer and closer and closer to that 1.33. Now, what if we did this exact same problem, but we actually chose the right endpoints as our sample x to plug into our function? Let's see what that looks like. So we're still going to use that uniform partition. Delta xi will be b minus a over n, or 1 minus 0 over n, or 1 over n. Each xi is going to be a, which again is 0, because we're doing the interval from 0 to 1, so we're starting at 0, plus I delta xi. So 0 plus I delta xi is 1 over n, so that gives me that I over n, just like it did in the previous example. But now our sample point is going to be the right endpoint instead of the left endpoint, so it's going to be xi. So xi, we just found here, is I over n. So now I'm going to do the same thing. I'm going to take the area, which is the limit as n goes off to infinity, of the sum from 1 to n. Remember, this is the height of the rectangle times this is the width of each of those rectangles. But now my xi star is I over n. So the height is the function evaluated in I over n using the right endpoint. My delta xi, however, is still going to be that 1 over n. And so now there's my 1 over n for my width. My height is the function evaluated at I over n, so it's I over n squared plus 1. So this is the height of each rectangle times the width of each rectangle. Now, just like before, this 1 over n has no bearing on this summation whatsoever, so I'm going to pull it out. I over n squared is I squared over n squared plus 1. The summation of these two terms being added, I can just take the summation of the first plus the summation of the second. And as previously, this n squared, this 1 over n squared, has no bearing on the summation whatsoever, so I'm going to pull it out. Now, these are summation formulas that we've discussed before. We have a formula for taking the sum from 1 to n of I squared, and we have a formula for taking the sum from 1 to n of 1. So this summation right here is n times n plus 1 times 2n plus 1 all over 6, and this summation right here is n. And don't forget I have that 1 over n squared there. So now, again, this n and one of those n's is going to cancel, and so I have n plus 1 times 2n plus 1 all over 6n plus n. Like I did before, I'll find that common denominator. Once the denominators are the same, I can add their numerators over that denominator, and then combine my like terms, which is just 2n squared and 6n squared. So now the area under that curve is the limit as n approaches infinity of 1 over n times 8n squared plus 3n plus 1 all over 6n. Let's go ahead and distribute that 1 over n in. And this, again, is a limit at infinity. We have a little trick where we'll divide everything by the highest power of n from the denominator, which is n squared, and reduce. And now we're ready to take our limit. The limit as n goes off to infinity of 8 stays as 8. 3 over n goes to 0. 1 over n squared goes to 0. 6 stays as 6. And look at that. We got the area underneath that curve to be 4/3 again. So it really doesn't matter if you take the left endpoint or you take the right endpoint. If you really want to, you could go back and do the whole thing using the midpoint, which is xi plus xi minus 1 all over 2, and do the function evaluation that way. But one thing that you're probably going to notice is that choosing the right endpoint tends to be just a little bit less work than choosing anything else like the midpoint or the left endpoint. That's it for today. See you next time.